Hi, everybody. Welcome to lecture 4 of the respiratory system. And in this lecture, we're going to talk about the processes of respiration in terms of the gas exchange and some of the physics that underlies ventilation. So remember that we talk about respiration as the exchange of gases between the atmosphere and the body cells, and we've broken that down into a couple different components: ventilation, external respiration, the transport of O2 and CO2 around; internal respiration, the exchange of gases at the tissue level in the systemic circulation, that is, delivery of oxygen to your body cells. And then last but not least, what drives all this is that process of cellular respiration, which happens at the cellular level with the mitochondria. So ventilation, strictly speaking, is breathing, and it's the movement of air in and out of the lungs. It's controlled by these pneumotaxic centers that are found in the medulla oblongata and the pons. And so we have neurons there that are dedicated to monitoring inputs from chemoreceptors in your circulatory system. There's these receptors in the aortic arch and the carotid artery, and they're constantly monitoring CO2 levels really as a function of pH. Okay, so there are inspiratory and expiratory neurons, and so those inspiratory neurons fire action potentials via the phrenic nerves and motor neurons traveling down to activate the contraction of the diaphragm, and then also the external intercostals. Okay, so if you remember, the intercostals are those muscles that weave into the rib cage. The breathing autonomic nerves of the breathing of the respiratory system involve the phrenic nerve, but also the vagus, and then these posterior thoracic nerves, and they're all involved in activating those muscles that allow the movement of the rib cage. So as you increase stimuli, the muscles contract, and you can increase lung volume, and that is how we control ventilation. Well, understanding how we actually get air into the lungs seems straightforward enough, but it also involves a little bit a closer look at those gas laws. All right, so remember that when the lungs are open, the external pressure at sea level would be 760 millimeters of mercury, or 1 atmosphere pressure, right? 101 or 101 kPascals. And that's what's outside of you, and that's what's inside of you. All right. Just like if I blow up a balloon, what's the pressure outside the balloon? Here, I'm holding the balloon up. Outside the pressure is 1 atmosphere. What's the pressure inside the balloon? Now, you may make the mistake of thinking that the pressure inside the balloon is higher, but it's not. It's actually identical. And you can tell that because what's the balloon doing? Nothing. The balloon is just sitting there statically, not moving. If it was expanding, I would know that the pressure inside the balloon was greater than the pressure outside the balloon. If it was contracting, vice versa. So the interior pressure of your lungs at rest is 760 millimeters of mercury. And that functions in accordance with something called Boyle's law. We say it obeys, or it's an obeisance to Boyle's law. And Boyle's law is pretty simple. It says that the pressure and volume relationship in situation 1, P1V1, equals the pressure volume relationships in the second circumstance. What do I mean? Well, you can see in our illustration here that as I compress the piston in the GIF here, what happens to the pressure inside? Well, of course, it increases, and we all knew that. We know that intuitively. Conversely, as I increase the volume of that piston, or the chamber the piston's compressing, what happens to the pressure? Well, it goes down. Well, the same thing's happening in your lungs. And pressure and volume are going to vary at an indirect relationship, right? So in your lungs, at rest, the interior pressure is 760 millimeters of mercury. when you decide to breathe in, the vagus and the phrenic nerve activate the diaphragm. And that diaphragm, when it contracts, actually pulls down, and it increases the volume of the pleural cavity. Right? It drags those lungs with it. So it increases the volume of that space. All right. So if once I've increased the volume, what's going to happen to the pressure on the interior? Well, the pressure is going to go down, and it actually drops down to something like 758 millimeters of mercury from 760. Doesn't sound like a lot, but that decrease in pressure creates a vacuum, and that's what allows you to suck air in. Now you can further increase that with a maximal inspiration, and that's when you would activate those other muscles. The sternocleidomastoid, remember that's the muscle that's connected to your, what is it, the occipital meatus? Auditory meatus? No, not the occipital condyle, and it's actually it originates there and then it terminates or it inserts on the sternum and it actually pulls your sternum up. So when you breathe in, one of the first things that happens is your neck muscles pull that sternum up, and then you have these external intercostals that open it up. Your pectoralis, major and minor, also help open up that cavity, and that just helps increase the volume internally of the pleural cavity, the pleural space, and increases the volume or the vacuum, or lowers the pressure. So there you go. Boyle's law. Live it, love it. So ventilation is defined by inspiration and expiration, and your lungs have like an elastic character to them. So without any effort, they will recoil. As they recoil, they'll blow air out, and that would have you when they recoil, the pressure in the interior. I'd be decreasing the volume, and so I would overcome the external pressure of the normal atmospheric pressure, and air moves out. Now I can also force expirate, and then again I'd be using the internal intercostals, and they would pull that lung rib cage down, and also abdominal muscles. So when you breathe out, you're going to use muscles of the abdomen as well. And so I don't know if anybody's tried breathing fire, but it looks like fun. Of course, what's going to happen when you try it? You're definitely going to burn your face, so don't try it. Next, internal respiration. So I've got ventilation, and I've exchanged gases in the lungs, and this involves the diffusion of gases from the alveolus into the bloodstream, and from the bloodstream out into the systemic tissues. Remember that it's all a function of the partial pressures of gases. When I breathe in, I've got oxygen-rich atmospheric air, and with relatively low CO2 concentrations. And so O2 goes into the blood. The blood itself, though, has high concentrations of CO2 in the lungs, and so I have an exchange there. I also will take that oxygen out to the tissues where they're starved from oxygen, and they've been building up CO2, all due to the process of cellular respiration. Okay? And so remember that these gases obey their concentration gradients. We could talk about them in terms of partial pressures. And what's driving it is this production of CO2 in the mitochondria and the use of oxygen to make ATP. So, cell respiration in a nutshell. Of course, I take glucose and oxygen, I turn it back into CO2 and water, and then I make all this ATP. But it's a little more complicated than that, so I'd expect you to have a slightly deeper recollection of the facts. Remember that the first phase of cell respiration is anaerobic, and the process is called glycolysis. And in glycolysis, I take glucose and I split it into two pyruvate molecules, two pyruvic acid molecules. This happens in the cytoplasm. It makes 2 ATP. There's another part of this cycle called the transfer reaction, where I take pyruvate and I turn it into acetyl-CoA and take it in the mitochondria. I'm not worried about that. But in the aerobic phase of the Krebs cycle, I'm taking that pyruvate, which has now been turned into acetyl-CoA, and I combine it with oxygen. Now, one of the products of this is carbon dioxide. All right. So remember, in glycolysis, I've broken down glucose, so I've taken that reactant. Now in Krebs cycle, I've used oxygen, and I produce CO2 here. So the Krebs cycle makes these electron carrier molecules like NADH and FADH2. It creates a hydrogen ion concentration gradient, and it also makes 2 more ATP. Now the big payoff for this, and of course Krebs is happening inside of the matrix of the mitochondria. That's the intracellular space. And what happens is during the reaction, it pumps hydrogen ions outside into the extracellular space. Now those hydrogen ions want to come in, and they come in through the ATP synthase. And so these electron carriers, NADH, FADH2, transfer electrons via hydrogen ions. They turn that ATP synthase into a bunch of ATP. In the end, oxygen accepts the electrons. It's the final electron acceptor in the chain, and it accepts them when it binds to hydrogen, so I make water in that final reaction. So, in total, I can make 36 to 38 ATP through cell respiration. That never really happens. It's the theoretical yield, but that's where all the CO2 comes from, and that's why I need to use oxygen. It's a lot. See you on the other side.